I'm part of the technical product marketing team here at Confluent, and I'm super excited to be joined by Justin today. He's a technical lead software engineer at Yelp. He's been there for about 4 years and an avid member of the community of Kafka. So super excited to have him, and I think you'll learn a lot from him. Today we're going to talk about messaging done right and how Yelp leapt to microservices with more than a message queue. We will have this recorded, and the slides will be delivered to you as well and made available to everyone on confluent.io. This is part of our Streaming in Action series, so we have a pretty cool couple of talks lined up after this one as well, going into how you might look at a streaming platform. It can be tricky for most. It's a new concept with many different angles and lenses that you might want to look at it. Is it messaging done right? Is it Hadoop made fast? Is it ETL as a platform? What is this new thing? What can I do with it? And that's really what we're here to talk about with the help of some of our awesome community members. There's a pretty cool VR use case we'll go over next week and Pandora the following week. So please come back if you enjoy this one to learn some more from some great people. So to get started with today, here's a quick look at the agenda that we'll have. I'll take the first part, talking about how a streaming platform is messaging done right. We'll go over, what a messaging queue is, gaps you might run into in production, and if we were to dream up from scratch what a great messaging queue would be, what it might look like. And then we'll hand it over to Justin, who will talk about how Yelp uses Kafka and made the move to microservices to really have a real-time data pipeline for their organization, and then the benefits that they've achieved with that. So some really good enlightening stuff there. I think Justin's great, and you'll learn a lot from him as well. So to get started, I think it's really good to orient ourselves around this definition of a messaging queue. So I tried to pull this from Wikipedia, and they use a queue for messaging. Like, really, we're going to use the same words from it in the first definition. I think that's cheating and kind of first grade level no-no. But maybe looking at it a better way is how people are actually using it. And so if we take a messaging queue, what you're really trying to do is decouple your producer and consumers of data. So you might do this for a web app that has a massive amount of writes coming in to get to maybe a relational database at the end there. You might do this for an Internet of Things monitoring tool where you have a MQTT coming out and you want to get that data into a monitoring tool eventually. So there's a variety of ways that you can throw these into your architecture, and some make sense and some certainly don't. And it's all about the right use case. But overall, what you're trying to do and what you're trying to achieve is you want to decouple these producers and consumers of data, and that gives you a little bit more predictable performance. Maybe your old relational system isn't able to keep up with something, so you can plug one of these in to really offset that and create a more flexible architecture as well, giving you the ability to add more things to it and remain relatively simple. And this is all good, I think, really in theory. It's definitely an interesting concept. Messaging queues have been around forever, really since before I was born. So plenty of things to do there. And definitely some people that are running them in production and being successful. But what I want to talk about here is a messaging queue at scale. So as an engineer, we always have to think, this thing's great in theory and maybe on our laptops, but how can we do this at scale? And what complexities might that introduce and what we have to, plan for. So the first is kind of our example app here, where we have a broker with multiple clients and multiple consumers of data. And what you might notice first, or one of the better engineers around us might notice first, is we have a single point of failure here. So messaging queues really aren't designed to be distributed. And with that comes the risk of failures. Easy to kind of orient ourselves around, and so maybe we introduce something like a standby broker as our first next step. This is helpful. It's good to do, good engineering, and it can help us achieve high availability if anything was to go wrong. Maybe we decrease our time to get back up and running. Good, well thought out plan, but again, it's another thing to manage. We're not really solving the innate problem itself. We're just introducing more complexity to it. And it's good to do, it helps you sleep better at night, but what are you really achieving and what are you using for your data? And Perhaps in a message queue, it's pretty strongly reliant on a FIFO ordering. So as the first thing comes in, the first thing comes out. What if one of these brokers isn't able to keep up? What do we do then? And we have to think about adding more brokers to the system to drive that throughput home and be able to support the architecture that we need to and hit our SLAs and all that goodness. We don't want any of those queues to fall over and cause some downstream system to have some pressure. So we get this, and that's pretty complex, right? We don't really want complexity when it comes to distributed systems that are complex already. So there has to be a better way, right? That's really the thought and the mindset to be around. And as most engineers, there's always a better way, and we'll figure out how to make it better. So as we look at a messaging queue, I think there's really three categories that we could look at. They can be unwieldy to scale, performance could overall be better, and we want to actually use the data. We're not just trying to move it from one place to another. Ideally, we'd add something into there to be able to leverage that data to create something better. And if you want to dive more into this overview, here's a really good white paper from Hans, one of our awesome SEs here, with a link as well. But if we're trying to, look at this long term, we're really trying to consider how we might do something better. And with a messaging queue, it's good for maybe some small use cases, maybe some complex routing, but at large, there has to be a better way. So if we start with our messaging queue and, we're dreaming it up maybe as Jay did a few years ago, we start with a publish and subscribe model. And then we kind of think about how we want to add to this. What value do we want to create? And I think there's a few key things here. So ideally, we're creating this centralized source that everyone can use. And because of that, they'll want to connect whatever they need and will become quickly reliant on it. So we really want to drive home kind of replications, common high availability practices, multi-data center solutions, things like that to become out of the box. And I think the other thing to consider here is, as we're thinking about it, we really need to re-architect our system. We don't want queues to be the idea of scale. We want something like partitions really to introduce that and to offset that complexity in a scalable fashion. So what we've done is kind of started with our publish subscribe model, and we added scalability. That's pretty cool. That's something that we definitely want in our solution, especially today when we have a massive amount of data coming at us everywhere all the time. And so next on our list of dream scenarios, maybe we want to make sure we can evolve our infrastructure. I think Justin will talk later about how they've quickly changed their infrastructure pretty repeatedly over the years to optimize for their use case. And I think that's a common thing that people have to live with in today's world. It's so fast moving. So maybe you want to change the database that you're using. Maybe you want to add search. Maybe you want to just recover an entire database. Even testing out a machine learning library where you want to send data to TensorFlow and see what you can play with there. Essentially, you just want to do something new. And so in order to do that, you really want to make use of this log of data, this source of truth of events over time. And you want to have the ability to store data and rewind and replay that data as you need. So really having control of your data, and what you want is true storage. Similar to a database in nature, you want something you can persist to and trust to own that data so that you can leverage that for better decision making down the road. And then finally, we wouldn't be here if you weren't trying to use that data in some way. So why don't we take the ideas of this messaging queue that can scale, that has true storage, and figure out a way to actually use that data as it arrives in real time to do more interesting things with it, maybe surfacing it to our users for a recommendation, or simply keeping a dashboard up to date in the moment. There's really limitless possibilities, but we want that real-time data to be accessible to everyone in our team, in our organization, and then we want it to be accurate as well. So some critical things there. And lastly, I don't know about you guys, but we don't want to manage additional things. Additional overhead to the system is never good, right? It goes back to that notion that this should all be simple, is really the mindset there. And we want to build applications. We don't want to build clusters. And so to think about what we're adding there is really something, I think twofold. I think there's this notion that we want to add something that's like a database, maybe a materialized view of sorts, and then stream processing as well. So as we move to this world of real time, how can we write continuous queries that are interacting with data as it arrives and sending that data out to our users, be it an aggregate or a session? What can we do with this data to make it accessible and useful and valuable to not only our team, but our end users as well? And so we're adding stream processing, and I think this is where kind of everything culminates. We culminate into this idea of a publish-subscribe model that can handle data integration. We can have scalability, something with partitions that's designed from the ground up to really scale. And what I mean by that is a distributed nature that's really fault tolerant and can survive a distributed system. And we need to have something that has true storage. The value of the data, especially in an ordered system, grows exponentially. So we can understand what happened, when it happened, and replay that data to have that source of truth constant across any system is really powerful. And then finally, we want some way to interact with that data and make it valuable. And that's really stream processing, and stream processing in the most simple way possible. And I think by having that right at the system of our streaming platform, that makes it the easiest way for any developer to really make use of that data. So what you get at the end is really the streaming platform, and Kafka is the most popular streaming platform. I don't think there's any arguments there. It's had a rapid rise of growth in the last few years. So to go through this a little bit, we have whatever data source we want. We want to connect that data through our Connect API to get it into Kafka, do something with that, something cool, something interesting, something valuable, to make it either send it back out to an application or send it to a downstream system that makes sense, which we do again through the Connect API. So you get this really powerful thing that can scale and remain simple at scale and provide value to your users in a really timely way. And I think a lot of companies have started to realize this. If you kind of orient yourself around this architecture paradigm, it's really a way to simplify your infrastructure and provide scalable real-time performance consistently and reliably. And then by having that central source, you'll find that developers want to access and use that data, and we'll have better developer productivity is the hope there. And I think Justin will kind of allude to this in some of the cost savings as well, but there's really a notion that by giving people freedom and the right access to what they need, they should be able to develop quicker and build that kind of functionality that today's apps are trying to deliver. And then lastly, this one's interesting to me. I think being flexible for the future is critical for how we have to think about things today. We're constantly introducing new technologies, be it a new machine learning algorithm we want to try, or a database maybe that makes more sense for us, or adding a search index or a caching layer. How can we build off of this system to make sure we're ready for the future and whatever that might require? And I think a lot of companies are realizing this. Here's just a quick overview of a few that have kind of made this leap to Kafka. And Netflix, for example, is supporting 1 trillion messages a day, powering their data pipeline with Kafka to make use of data around their organization and give it a single access point for what they need. Line is doing streaming ETL on millions of messages daily with Kafka's Streams API, which is incredibly powerful and simple. And the New York Times is using Kafka for a source of truth, storing every article since 1851, which is insane, to be able to have a home for that and to be able to access that very easily across the organization to get it where it needs to be. And there's people like Justin that are doing cool things with it at Yelp. And so at this point, I think it's worth handing it over to Justin to hear some really interesting things that they've been working on over the years. Justin?
Thanks, Greg. I'm Justin. I'm a tech lead here at Yelp. I'm working on our data pipeline and also our experimentation and metric system. To introduce Yelp, our mission is to connect people with great local businesses. To give you an idea of Yelp's scale, we're currently in, as of June, the ComScore Top 20 for U.S. multimedia digital media properties. That puts us slightly ahead of companies like Zillow, Netflix, Pinterest, and TripAdvisor. So we're operating at considerable scale, and what kind of makes us a little bit unique is that we've been transitioning to a mobile-first approach where we're really focusing on our mobile application because our mobile users are very, very engaged. They're about 10 times as engaged as our desktop users measured by page views. So that's been a really interesting transition, a little bit different from the metrics collection side. So our data pipeline and why we built it, it really starts with our monolith, which is the repo that we were using at Yelp for all of our deployments. In 2011, we had really a single repo with all of our code. It was about 1 million lines of code, a little bit more than that even, with all of our developers working in that repo. The issue that we started running into was that it didn't really scale up as the number of developers scaled up. It became really hard to push code, to test code, and to iterate and do code reviews and stuff like that because there were so many people trying to work in the same code base. You had kind of like constant conflicts, merging, and then also like the length of the runtime for the test suite became really, really high, and there were just constant problems around scaling it. So what we started looking at was how to transition to a different way of doing it. So we landed on services and quickly built out a pretty advanced service-oriented architecture. And in 2014, we had around 150 production services that were running. Yelp main, our monolith still continued to grow. We still have a lot of developers working there, but we started to break things up really, really significantly, which introduces a new set of challenges. I think they're a better set, but you still have challenges there. So one of the challenges, and I think probably one of the largest, is really around the value that you get out of communication. Inside of a monolith, you don't really have to do any communication outside. You can kind of have all of the code talk to all of the other code, and there's a lot of value there. What Metcalfe's law says is that the value of a communication network is really proportional to the square of the number of connected communication devices. So in a service-oriented architecture, you could kind of think of a connected communication device as a service. So the value of a service-oriented architecture could kind of scale proportionally to the square of the number of services that are able to talk to each other. And that kind of follows because if you think about it, being able to talk to a service and have that service talk back adds value. So like if you can't really efficiently talk to everything, then it becomes hard to actually add a lot of value. So when we think about this in the context of like REST APIs and how you would usually build out a service-oriented architecture, what you come to pretty quickly is limitations around that communication. So at 150 services, if we were building bidirectional communication, so that would be like a service talking to another service and that service being able to talk back, we'd have 11,175 of those. If we did it omnidirectionally, which would be like a service makes a REST call to another service, and if that service wants to talk back, it has to make a REST call, we're up to 22,350 connections. And that's pretty hard to manage. So the other challenge is around the data. So in particular, two things here would be the source of truth and dealing with joining. So for source of truth, it becomes really, really difficult in a large service-oriented architecture to figure out who actually owns what data and what is authoritative and what's not. And the reason is you have to cache things to make it performant enough. So what you could end up with is different services having different views of the data set. And that makes it very difficult to figure out what is actually true and what isn't. And you could end up in a situation where you're making a API calls to multiple services and they're returning slightly different results for things that they have slightly different views on because of when they last updated. And then you kind of have to have the service that's aggregating those results makes some value decision over which one really is right. And that's just hard to get right. With joining, there are many, many challenges around scale and how to do that efficiently. Like if you're trying to make individual service calls every time you need to join data, you're going to end up making tons and tons of service calls. It looks a lot like the N+1 query problem with databases. It's hard to do it efficiently. So when we start thinking about what reasonable things are, it's also kind of tough for the average developer to really reason about it well. This is something that actually happened when we were looking at some data warehousing applications and being able to synchronize things. My team went to a developer in a different group and said, hey, I want to query your service. I want to get every review every day, and I want to get the metadata that you have about that review. They're doing some scoring. And initially the reaction was, oh, sure, yeah, you can totally do that, no problem at all. Then we rephrased it slightly to actually what I want to do is make more than 1,000 requests per second to your service every second forever. And really, with the number of reviews we have, it'd probably be closer to 2,000 requests a second now, if nothing ever went wrong. And the developer kind of immediately said, oh, wait a second here, because now I'm actually going to have to deploy more service instances and potentially have additional maintenance overhead, and I might have to deal with some database scaling to make that actually work. So let's rethink that. And it's really just a different way of asking the same questions, but I think it illustrates kind of what problems you hit concretely as you scale up with services when you're not really fully baked yet on how to deal with all of the problems. So as far as potential solutions go, a couple of things that come up pretty quickly are, what if we were to implement a raw bulk data API and we could then potentially get all of this data out of other services, and it would be more efficient because for some of these joins, we could just get all of the data at once instead of having to issue individual REST calls for each piece. And then ultimately that sort of devolves into like, what we should actually do is just expose an interface so that we can query all of the data in all of the services arbitrarily. And the problem with that is that you start to really break down the service boundary. And one of the things that services buys you is clean boundaries and interfaces across the code so that teams can develop independently, ideally without breaking each other's work. And as the service boundary disappears, you end up with all of the coupling problems that you kind of start to run into in very large code bases. So we didn't want to encourage that. The other problem, and this is really for things like machine learning applications and bulk data applications, is around what to do like if we were to take database snapshots and just pass them around. And really part of the issue here is that sometimes the database, it doesn't really have quite enough context, some additional context from the application to tell what's really going on. And that would be things like flags or enums, pretty much anything that's not really completely stored inside of the database. We kind of see this problem a lot, and any kind of like binary flag column becomes really, really problematic when you're trying to interpret another service. This is partially worked around by just making the data more readable, but again, at scale, that's kind of tough to do. Another big issue that we saw when we started moving to the service-oriented architecture is difficulty managing failure, because fundamentally, as soon as you move to services, you have introduced the network, and the network sometimes fails, even reliable networks, especially when you have multiple data centers involved and long latency links like international data centers or cross-country, that kind of thing. This is kind of a common pattern that we noticed for notification that some developers would try. So what you see here is really a developer creating a session and adding a business to it. And this is sort of like, I guess, faux SQL alchemy, standard transactional database business edition. and then trying to send a notification right after. The issue that you run into here is if the session commits, but then the notification fails, the service will never really find out that that business was added. And that's problematic. You may have to go back in and add some kind of batch to periodically check and see what businesses are out of sync, and then do some kind of process to correct that. The other thing that we'd see is the same code being refactored slightly so that now the notification happens inside of the commit. This also is prone to failure in a different way. And here what can happen is that the business notification is sent to the service saying that, hey, this changed, but then the session commit actually fails. So the change is never committed to the database. So now the service thinks the business exists, it doesn't exist, and potentially starts processing on it, and maybe even, depending on what it is, starts reporting it as something that exists when it doesn't. And this can kind of create all kinds of cascading problems across the infrastructure. So to start solving these problems, I think it's really helpful to think about like how you'd solve them generally. And what we started looking at is converting to a messaging bus-based architecture instead of having each service talk to each other independently. And what this buys us is a reduction in the number of connections across things from n squared to n. So instead of having those 22,000 some connections for all of the services to talk to each other, we can reduce that to just 150 with 150 services. And what this buys us is a much simpler architecture, and also kind of transitions toward a more pub sub based approach where each service is really saying what happened as kind of a fact, and then other services are listening for those facts and reacting to them. An example of that would be in the context of Yelp, something like a review service saying this review was written, and then a number of other services saying, oh, now that review was written, I want to react to that and respond appropriately. Why Kafka for this application? Kafka is definitely a messaging bus, and it has a bunch of really, really great qualities that we look for in any kind of messaging bus. In particular, the performance of Kafka is insanely high. Like, you can get hundreds of thousands, millions of writes a second, and it's not really that hard to get there. It makes a lot of the scaling challenges go away because it's just great from the performance perspective. Persistence is, I think, underrated here. And I say that because with Kafka, we're able to persist all of the messages that we've ever sent through the system, and that means that we are much more resilient to failure. When you have hundreds of different services running in production, what you end up seeing is there's always things breaking, at least in places. So in order to really make things reliable, you have to be able to reprocess things after something goes down and comes back up. Like, we wouldn't want a service that is waiting for review notifications to never get that review notification because it was broken because we were deploying some code and we had to roll back. Instead, we wanted to pick up right where it left off when we fix the problem and have that just work. And we're able to get that with Kafka really easily. The reliability part is really related to the persistence part, but also I think it has to do with the next point, which is replication. And that is, by replicating partitions across many nodes of the cluster, we're able to have much greater overall reliability. Like, even though we tend to operate things in CP mode, we're able to get greater availability because of this replication. And the scalability piece, I think, also is heavily related to that, again, because we're able to replicate, we're able to distribute load across many machines, and that helps significantly with scale. We actually run quite a few Kafka clusters as well across different regions to help out with this, and that has worked great for us. And the last piece that I want to touch on is log compaction, and I have a slide to explain that since it gets kind of in depth. But the basic idea is, for log compaction, is that you have offsets and keys for each message. The offset is the position where the data was written into Kafka. The key is kind of like a key in a key value store, and the data is the data that corresponds to it. So every Kafka message can have a key and a value. And when you turn on log compaction, the guarantee that it provides is that you'll always have the last message that was written for a key in the topic. That will always be retained. And that provides some really, really nice properties, especially when you're dealing with streams as tables or tables as streams. That's kind of a good way to guarantee something called stream table duality, where you're able to replay a stream and reconstruct a table, or take the table and then convert it back into a stream. So roughly the way that the log compaction in Kafka works is that it scans through each topic and looks for all of the keys, and it finds the latest offset for each of those, and then it copies the data into a new topic, making sure not to copy things that are before the latest recorded offset. So you can end up with multiple copies if they're after the compacted point, but you will drop data before that. And again, when you're dealing with a database application, this makes sure that you have one message for every key that you've ever written in the topic, which is really, really helpful. Haven't seen another message queue offer quite the same thing, but it opens up a lot of possibilities, which I'll get into. So what is our data pipeline really? When we're looking at it, it's really a protocol for communication. And it's kind of composed of a few different things. One is Kafka, which we've touched on. The other is Avro, which is a schematization format. It's an Apache project that has some interesting properties. Basically, it lets you convert data back and forth. So if you write it with one schema ID, you can always read data in our system with that same schema ID, even if the schema changes. We maintain some compatibility guarantees, which I'll get into. And the other thing is that we maintain a set of simple guarantees around this communication that is able to let you build really robust applications on top of it and treat it more like a platform than like an individual service or a collection of services. So to get into the guarantees, the first two that we offer are guaranteed format and a guaranteed compatibility. This goes back to the Avro format that I was talking about before. All of our messages are guaranteed to be in Avro. We wrap all of the messages with an envelope that contains some metadata about the message, like the timestamp that it was written. We also include a UUID, what type of message it is. We support a few different messaging types. And some additional metadata about ownership and documentation. That format makes sure that everybody that is writing or reading into the system is doing something in a consistent way. We have a service called the schematizer, which is responsible for maintaining the format and compatibility guarantees. So what happens as a user is that you start consuming data from a topic and you've started using a schema. In the background, if a new producer comes online and starts writing data into a topic, it could be using a different schema. As long as it's compatible, the schematizer controls which topic data is written into. So we'll guarantee that you'll always be able to read out of that topic once you've started consuming from it with the schema. So what the diagram here is showing is that as a consumer, when you start reading with the first schema, what will happen is that as new schemas are created, your consumer will dynamically load those schemas and decode messages with them and then convert the data back to the format of the schema that you're using to read. So that ensures that as an application developer, you don't have to worry about any schema changes breaking what you're doing. So that's the guaranteed compatibility part. Next is guaranteed data availability, and this is really about having one of everything. This is the guarantee that you get from log compaction. And one of the chief applications that we use this for is taking all of the database updates that we make throughout Yelp and publishing it to Kafka. And with this guarantee, we're able to make sure that anything that has a primary key assigned to it gets published to Kafka with that key, and that means that we always have the latest version of that database row by primary key inside of the related topic. So what that allows us to then further guarantee is that if you replay that topic from the beginning into a key value store and you're making an update of the contents of the key value store for every key, what you'll end up with at the end of that process is the state of the table as it exists today. So you can replay that stream of updates to reconstruct the table. Again, that's stream table duality, and it's a really, really powerful concept. It means that if you're tailing one of our database topics and you're doing some kind of machine learning application, when you get done tailing that topic, when you reach the tail, the table contents are exactly the same as they are in whatever the upstream is. So that gives you a very strong guarantee for any of those bulk data applications. And because you're doing only differential updates, it's also very efficient. So the data pipeline, again, is really all about the data. And there are two components. Our schema store, which we call the schematizer, and Kafka are the core components of this system. And really the schematizer is sitting around Kafka to try to provide almost like air traffic control for creating and registering schemas, assigning topics, and doing that so that we're able to make sure that these guarantees are upheld. This is how we actually use this system in practice. So again, at the core, you have the schema store in Kafka, which are doing that air traffic control role and making sure that data is written in a way that we can maintain our guarantees. In the periphery, we have all of the applications that we have implemented. So we have application event logs, which are basically the operational logs that are being generated by the website, and also metrics logs, event logs, things like that. And then we have MySQL updates, which are being generated and then published to Kafka, as I described. And then we also have code and stream processing applications that are generating messages and publishing them to Kafka. On the other side, we have different data syncs where we're writing the data, and additionally, it's also going into additional logs in the code and stream processor again, and that allows us to kind of implement the whole thing recursively. So we may have an application that is writing something out and then processing it in the stream processor and writing it back to Kafka, and then processing it again on a stream processor and writing it back to Kafka, and then ultimately putting it in Amazon Redshift. So the kind of interesting thing here is that if you write something into Kafka using any of the schemas that we have, you're able to immediately take that data and stick it into MySQL or put it on S3 and archive it or stick it into Amazon Redshift, and you don't have to write any code to do that. So it starts to make it really powerful as far as what you can do with data just by writing it once. Here's a concrete example for what we're doing with business changes. Whenever a business changes in MySQL, we take that and we pass it through a stream processor, and that stream processor makes the data more understandable for human users. What we actually do is we look for things like flags columns and we expand them into Boolean fields. We take a few enums and expand those into strings. It makes it very, very easy for the final application to work with it. We also inject some documentation from our database models. At that point, that same data goes into all of these systems. So it goes into Amazon Redshift for data warehousing. It goes onto S3 for permanent archival. It goes into Elasticsearch. This is how we actually power search at Yelp. And it goes through some other code where it's processed for additional systems, one of which is Salesforce. So we actually have a Salesforce connector that will read these same business updates. So just by building out a MySQL connector, we're able to then take business updates and shuffle them all of these places. And we've had in the past systems to do each of these things individually, but we've been able to consolidate onto this platform, which has been incredibly valuable. So where are we going? I think it's kind of interesting to think about re-architecting in an event-first way. And that kind of makes the event log the system of record for the company. And what I mean by that is right now, you could kind of think of a typical pattern would be a web worker processes some task and writes whatever the output is into a database. So this could be like a post request comes in for a review, and that review is taken and written to a MySQL database, and then we serve traffic from that database. The direction we're heading is that instead of doing it that way, the web worker would write the review to Kafka, and then from Kafka, it goes into the database for persistence. It also would potentially go through a SQL stream processor where it would be written into a materialized cache. And then what the website is actually serving is that materialized cache that we're keeping continuously updated from the event stream. So it's really doing a complete inversion of the way that we would do this, from the event coming out of the write to MySQL to instead the event triggering the write to MySQL, and instead of the cached view being generated at runtime, it's really generated in advance and updated whenever the data changes. And because it's all differential, it's again really, really efficient. This is the overall data infrastructure that we're working on building. Right now, this is kind of our medium-term roadmap. The basic idea is that, again, we have a bunch of different data sources connected on the left. One would be Yelp main, which is, again, our main monolith. All of our services are connected. We have a MySQL connector, and we're building out connectors for other data sources that we have, so that as an application developer, as soon as you have a data store, everything that you write into it is also automatically getting written out into streams. From there, all of the data flows into Kafka, and I think the most interesting part of this diagram is actually the middle, where we have the Kafka to Kafka connection. And I say this part is recursive in the sense that we could potentially process all of our Kafka messages repeatedly to build kind of very advanced processing topologies and kind of build out like a directed acyclic graph of all of the data flows that are happening. So we have two ways that we're supporting this today. One is PostWorm, which is a Python implementation that we made internally. The only thing that we really want to support there is FlatMap. I'd actually love to transition this to Kafka streams at some point so that we can not maintain it and also get more functionality. The other thing that we're maintaining is a Flink cluster today, which we are using to do advanced stream processing, and that's all written in Java or Scala. What we actually tend to want to expose to developers, though, is a SQL-based interface. So they're writing SQL. That SQL is operating on an input stream and then writing to an output stream and doing things like aggregation and filtering in a way that is really, really easy for the average developer to understand. So as a team, we're maintaining the infrastructure to be able to do the stream SQL. An average developer adds a SQL statement to a config file. We take that, deploy it, and produce a new Kafka output topic from it based on whatever information they want to be able to collect. And then the last part of it is really building out a variety of sync connectors as we need them. So that would be things like MySQL or Redshift, which I've described before, but also like Elasticsearch and Cassandra, and pretty much any place where we would want data. Ultimately, we'd like to be able to pass it and then get it there. And the value here is really being able to build out a data processing platform where if you get the data into Kafka, you can do lots and lots of things with it without writing any code. And similarly, if you want to build something to put data somewhere, it becomes then much easier to just build another connector, and then you have access to tons and tons of existing data that's coming from all of these different sources. So what we're seeing is really strong network effects, and I think this is similar to where Confluent is going with the Kafka Connect platform. So I'm also hopeful that eventually we'll be able to transition to that and stop maintaining so much stuff internally. And again, with the schematizer, we have that as kind of like the control plane for the whole system, deciding like how to do topic allocation, where data should go, and really also doing discovery and documentation. So how has this helped Yelp? We've seen more than $10 million in direct savings from this, and that's in terms of engineering time. We had many duplicative systems before doing the same kinds of stream processing. So writing data into Redshift, we had a system. Streaming data to Salesforce, we had a system. Putting data in Elasticsearch, we had a system. By combining all of this, we've eliminated most of those systems, and now we have instead fewer things that are much more generalized. It's kind of like, the way I look at it at least, is it's the difference between building a database and a data store specific to a single data type. Like, the database is harder to build but much more flexible, and you can do a lot more with it. The data store specific to a specific data type is a lot more expensive to build if you're doing a lot of it. So we've kind of standardized on building things that are taking in schema types that we support and then putting them in places, and that's been great from a cost savings perspective. The other thing that it's done is really generate higher quality data, metrics, and analytics. And this is really through enforcing things like documentation throughout the system. And we accomplish that with our schematizer. Like, we don't actually let you register schemas that don't have documentation. We require ownership, things like that. That makes it much, much simpler for teams to write high quality data. And we've started having some review process around schemas to make sure that if you're going to log something, it's of high quality and has the information that it needs. And really, what high quality data leads to is faster, better decision making. And I think it's still relatively early days for us compared to, say, LinkedIn, where a lot of this stuff started. But I think we're rapidly getting to the point where we're seeing really, really great tangible benefits from having built out this platform. And with that, I will turn it over to Garrett to close it out.
Thanks, Justin. That was really great stuff, and I think people got a pretty good inside look at Yelp and your infrastructure there. And definitely the benefits that you've gained are awesome. So to bring this kind of home before we get to a little quick Q&A, I think the high-level messages that we're all kind of relating to and bringing back is that you can decouple and modernize your infrastructure very easily with a streaming platform. Bringing many things to real-time data is really powerful. And opens up a door of opportunities for an entire organization, especially being able to have something building off of a messaging queue that's a little bit more able to scale and readily able to handle kind of fault-tolerant business application needs. And then lastly, we can do all of this, and Yelp specifically touched on this a little bit, but we can build streaming applications and data pipelines to really magnify what's possible and give access to everybody within that organization. And so it's a really interesting look at how we built on the concepts of a messaging queue to build into a whole streaming platform and the benefits that were gained with that. And this was just the first talk here. Next week at the same time and same channel, we'll be talking with Greg Fedor, who's a virtual reality expert. We'll talk about a little bit how you can think of this as Hadoop made fast, and some of the things that have evolved over time since Hadoop was first introduced in 2005. It's crazy how quickly that's happened. But how streaming platforms are really a next iteration of that, especially with stream processing. And then lastly, our kind of calls to actions here. I think there's a ton of good Yelp engineering stuff, especially on their blog. Definitely recommend checking that out. And Justin will actually be joining us at Kafka Summit 2, which is August 28th in San Francisco, which I highly recommend attending just to meet people like Justin. Plenty of good conversations and talks to be had there. And I'm sure some craft beers as well, which is always a good time. So at this point, we'll hand it over to some questions I have. And I think most of these are for you, Justin, if you're ready.
Sure.
Awesome. One of the things that's pretty specific to you is people were curious about Monk in your infrastructure and how that fits in.
Sure. I didn't get too much into Monk. Basically, what we are going to be doing with it, let me scroll back to the diagram so we don't totally lose context on that. So Monk is this point in the diagram. What we're doing is kind of on on-client aggregation. So we have quite a few physical machines deployed at Yelp, and the way that our log infrastructure works is that we run aggregators on each of those, and then those aggregators ultimately pass the data that they're collecting up to other aggregators and then on to Kafka. Monk is our aggregation layer. The other thing that we're looking to do with it is to actually kind of convert it into I would say the interface for all stream publishing here, so that if you're writing to a stream, you pass it to Monk, and depending on what mode you've selected, it either passes it to Kafka immediately, hopefully doing transaction management and stuff like that for you, or it aggregates it and then passes it on. So this is kind of the way that we do an AP versus CP mode. So it's in CP mode, it would go directly to Kafka and fail back to the application if something goes wrong. In AP mode, if Kafka's down or we're having a network partition or whatever, it would take the message, aggregate it, wait for Kafka to come back up, and then send it whenever it can. So slightly different guarantees. We want to have Monk be the layer to support all of that logic. And ultimately, the other thing that we're hoping to achieve with it is making it a little bit easier to do Kafka upgrades and support new features, since we wouldn't have to upgrade our application code.
Awesome. And then while we're staying on the same slide, we have a few similar questions. For instance, and I know you touched on this already, so apologies, but the role of schematizer, and then another question that I think you commonly get, any plans on open sourcing it?
Yeah, so schematizer, what we're doing with the schematizer is a lot of different things. Every schema in the system has to be registered. So if you want to write data, the first step in that is registering a schema with the store, and then that assigns topics. So as a developer, we really try hard not to expose what streams are topics or partitions or anything like that. Instead, you tell us what data you want to write or what data you want to read, and we figure out what the streams that correspond to that, partitions, topics, clusters, etc., are, and configure everything to just work. So the schematizer is sort of the control plane to make that happen. One of the interesting things that we've been doing is extending it out so that you can specify things like data targets. So what a data target would be something like an Amazon Redshift cluster. And the idea is that you declare inside of the schematizer that your cluster is interested in these schemas, and then the infrastructure will configure itself to get that data into your cluster for you. So it's all supposed to be declarative, and that also kind of feeds into our documentation system. So we can say, here's data that went into this Redshift cluster, and it comes from these upstreams. As far as open source, we actually open sourced a bunch of this stuff a while ago. It's available on Yelp's GitHub page. I would probably actually recommend trying to use the Confluent stuff instead of going to our stuff. The reason is it's very Yelp specific. I think the primary motivation for open sourcing it was to share some of the ideas in some of the code, and not necessarily to have people use it directly. I think actually a lot of the concepts are duplicated or otherwise implemented in the Confluent ecosystem. Like PostStorm has an analog in Kafka Streams. Confluent has an open source schema store. So I think it's possible to implement most of this way. So I wouldn't necessarily go with the things that we've open sourced. I would probably go directly with the Confluent stuff.
Cool, thanks for that. And what Justin's alluding to there is the schema registry that we have. And so moving on a little bit more to your deployment at large, people were curious about, if you're in the cloud, you mentioned you're across availability zones. Is that a span cluster, or what does that look like?
We are in the cloud. We're in AWS for the most part. We also have a couple of physical data centers still, but I think we're moving away from them as fast as we can. It's just taking a while. So our cloud deployment, we have I believe we're in 3 regions right now, and in each of those regions, we run Kafka clusters. We always deploy across AZs so that it's resilient to an AZ failure. We deploy in multiple regions so that, one, the latency is low. So to give a concrete example, all of our logging, like I said before, we have Monk doing log aggregation on physical machines. So all of the physical machines that are aggregating in US East will take that data and send it to a Kafka cluster in US East. And by doing that, we're able to cut down on latency and also run our application a little bit more resiliently as we shift traffic around and stuff like that. We don't actually maintain a big cluster that's cross-region just because of latency issues. What we have kind of settled on at this point is instead of maintaining a big cross-region cluster, having consumers in some regions read from clusters in other regions, or in the alternative, what we've been considering is doing some mirroring, sort of mirror from, say, the US East cluster into a US West 2 cluster to, again, reduce latency for some of these applications. I think that from our perspective, that's mostly a trade-off of like how many applications do we have that are doing these cross-region reads versus how complicated and expensive would it be to build an aggregator that was talking cross-region.
Cool. Thanks, Justin. And I'm going to cut us off here. I think there's a few more good questions that we should be able to answer over email for those of you that are left hanging. I apologize for that, but I have to be mindful of time. Is there anything else you want to add, Justin, before we cut out?
I think that's everything. And if anybody has any questions, I'll definitely be at the Kafka Summit in San Francisco. I'd be happy to take questions there, and I'm always happy to talk to anybody.
Awesome. I really appreciate it, and that's been a great part about it being a part of this community is everyone's so welcoming. So awesome. Good stuff, everyone. Thank you so much for joining. Same time next week with a new member talking about virtual reality and a little bit more about stream processing, which should be fun. And thank you, Justin. Super awesome hearing you talk. Thank you for taking the time.
Thanks.
Have a good